Dear students, Assalamu alaikum. Let's start lecture 23 of data structures and algorithms. We are working with trees and we use chapter 13 of book 1. In the last lecture, we were introduced to breadth first tree traversal algorithm. We were introduced to the heap. We learned how to add to, build and delete from a heap. And we examined all codes for time and space complexities. Now we take it up from where we left. Heapsort. This is a very important application of the heap. Given a list of n elements, step 1. Build a heap stored in a Python list. Let's call it my list. Length of the heap is n from 0 to n minus 1. For I from 0 to n minus 2, step 1. This means that every time we are going to increment I by 1. Sub-step A. Swap elements 0 and n minus 1 minus I. Length of the heap is now n minus 1 minus I. Sub-step B. Sync the root in the shortened heap. Step 3. Return my list to the user. It now contains the elements stored in ascending order. We are going to use Heapsort to sort the given list. So we start with the first element, which is 15. I have shown you 15 as the root node of the tree. In fact, in memory, 15 is the 0th element of the Python list in which I am building my heap. Then I take the second element, 21. I place it at the end of the Python list, and once I have added it to the heap, now I am going to restore the heap order property. So I will see whether 21 needs to rise, and it does. You see that the tree has changed and the Python list has also changed. The third element is 16. Here you see it appended to the list. Obviously, it gets appended to the tree. Now I check whether 16 needs to rise, and it does not. So I let it be. The next element is 2, appended to the end of the list. Now I check whether 2 needs to rise. It does not. So I let it be. The last element is 32, appended to the end of the list. I check whether it needs to rise, and it does. So 32 and 15 are going to be swapped. Now I check whether 32 needs to rise more. 21 and 32 are going to be swapped. All the elements of the input list have been added to the heap, and the heap is built. This list, shown here in the brown box, contains the entire heap. Now, how does Heapsort work? You can notice that the largest value is at the root. I delete the root, I get the largest value. Then I reheap. Again, the largest value comes to the root. This is actually the second largest value that was given to me. I delete it and then I reheap. I keep doing this and I keep getting a sequence of values in descending order from the largest to the smallest. What am I doing? I am sorting with the help of a heap. Now, the only thing that I am going to change here is instead of deleting the root, I am going to swap the value of the root with the last node. So when I start, I'm going to swap the value 32 with 15 because 15 is the last node. And you will see that at the end of heap sort, we will have a sequence in ascending order in the same list that now contains my heap. So it goes like this. I is 0 and you swap element at 0 and element at n minus 1 minus I. N is 5. 5 minus 1 is 4. 4 minus 0 is 4. So you swap the element at 0 and the element at 4. In simple words, you swap the first element and the last element of the heap. This results. And actually 32 has been deleted from the heap and the heap has been shortened. Now the heap exists from 0 to 3. That is why you see that the brown box has also shrunk. 32 has been deleted from the heap and 15 has been placed as the new root. So the ACBT is preserved, but the heap order property is a mess. So I check the children of 15. One is 21, the other is 16. Both are greater than 15. I have eyes for the greater child, which is 21. So I am going to make a swap between 15 and 21. What am I doing? I am sinking the node or sinking the root. So this happens. Now again, I look at the child of 15. 2. Does 15 need to sink more? No. Look at the list. The list has actually adjusted according to my swaps. So all that I wanted to do for I equals to 0 has now been done. I is now taken to 1. Now I am going to again swap the first and the last elements of the heap. The first element is 21. The last element is 2. What I am doing is I am deleting 21 and I am making 2 the new root. This happens. You can see that the brown box has shrunk again because the heap only exists from 0 to 2. 2 has two children, 15 and 16. Both are larger, but I am going to sink it towards the greater child, 16. So I swap 2 and 16. And the list has adjusted accordingly. Now, everything that I wanted to do for I equals 1 is done. I goes to 2. Again, I am going to swap the first and the last element of the heap. I am going to delete the node containing 16 and replace it with 2. This happens. Again, the brown box has shrunk. The heap now exists from 0 to 1. Does the new node need to sink? Yes, it does. Swap it with its child's value and the list adjusts accordingly. Everything that I needed to do for I equals to 2 is done. So I becomes 3. I swap the first and the last value of the heap. I am deleting the node 15 and I'm replacing it with 2. This happens. The brown box has shrunk to just one element. Only 2 is part of the heap. All the other elements have been deleted out of the heap. So since 2 does not have any children, I don't need to sync it. And everything that I was supposed to do for I equals 3 is done. Do I need to carry the for loop forward? If you remember, I told you that a single element is pre-sorted. Look at the heap. It has only one element. Do you need to sort it? No, you don't need to sort it. So the for loop discontinues over here. And now look at the list. It contains the input elements in sorted order. And this is what we are going to return to the user. Complexity analysis of Heapsort. The first part of Heapsort builds the heap. It takes O n log n time to build the heap. The second part of Heapsort does n minus 1 deletions. Each deletion takes O log n time. Time for the second part of Heapsort is O n log n. Since the two parts happen one after the other, their times are added. From this, I can say that the time of Heapsort is O n log n. You've already done sorting, and you must have noticed that most sorting algorithms are O n squared. But Heapsort is O n log n. This makes Heapsort the fastest sorting algorithm. What about space complexity? Heapsort uses a Python list of n elements to hold the heap. It builds the heap in this list. It sorts the element while they remain in this list. So this means that it is an in-place or in situ sorting algorithm. It uses a temporary variable for swapping. So the temporary variable is constant memory. We ignore that. But the Python list is of n elements, and from that we can say that space occupied by the heap sort is O(n). Now our topic is search trees, and we will use chapter 14 of book 1. Binary search tree or BST. A binary search tree is a binary tree in which for every node x the following is true. All nodes in the left subtree of x contain values less than that of node x. All nodes in the right subtree of x contain values greater than that of node x. An in-order traversal of a binary search tree yields a traversal sequence sorted in ascending order. Here is an algorithm to help you build a BST. There is a Python list called val which contains all the values that we will use to build our BST. We take the first value, val0, call the btree class init function and put this value in the root node. Then we run a for loop from 1 to lenval minus 1, and every time we take val I and add this node to the root, and then at the end of the for loop we return the root. This is how we build a binary search tree. But there is one thing here that we don't know how to do. How do you add a new node to the root of a binary search tree. Adding to a binary search tree. For input we get two things. Pointer to the root of the BST, we call it node. Value to insert, we call it item. First of all, we say that our parent is the node and added is false because we have not yet added item to the tree. While not added, so a while loop starts. A. If item is equal to parent.data, added is true. There is no place for duplicates in a binary search tree. So if an element is already part of the binary search tree, we never re-add it. This is what we have checked here. The A part, if it is true, this means that the item is already present in the binary search tree. Then we do not re-add it, we simply set the added variable to true. So when we will check the while condition, we will come out of the while loop. The second part of this while loop deals with the condition when item is less than parent.data. Data in the node that is given to us is greater and the item value is less. Now we check for the left child. If a left child is present, we update the parent variable. Parent is now the left child. If a left child is not present, we make a node, put item in it, and make this node the left child of parent. And now since we have completed the addition, we set the added variable to true. The third case of while deals with the condition when item is greater than parent.data. In this case, we check for the right child, and if the right child is present, then we update the parent variable to right child of the parent. If the right child is not present, we make a node, put item in it, and make this node the right child of the parent, and we set added to true because we have just added the item to the tree. Step 3 says return the root. This is how an item is added to a binary search tree. Let's build a binary search tree from the values given here. The first value is 60. I make it the root of my tree. The next value is 12. I compare it with the root. 12 is less than 60. I move to the left, but 60 does not have a left child. So I make 12 the left child of 60. The next value is 90. I start comparison with the root. 90 is greater than 60. I should move to the right, but there is no right child. So I make 90 the right child of 60. The next number is 4. Start comparison with the root. 4 is less than 60. Move to the left. We come to 12. 4 is less than 12. We should move to the left, but there is no left. So I make 4 the left child of 12. The next number is 41. Start comparison with the root. 41 is less than 60. Move to the left. We come to 12. 41 is greater than 12. We should move to the right, but there is no right. So I make 41 the right child of 12. Then we have 71. Start comparison with the root. 71 is greater than 60, so move to the right. We come to 90. 71 is less than 90, we should go to the left. But there is no left child of 90, so I make 71 the left child of 90. The next number is 93. Start comparison with the root. 93 is greater than 60. Move to the right. We come to 90. 93 is greater than 90. Move to the right, but there is no right. So I make 93 the right child of 90. Now I have 1. Start comparison with the root. 1 is less than 60. Move to the left. We come to 12. 1 is less than 12. Move to the left. And we come to 4. 1 is less than 4. We should move to the left. But 4 does not have a left child. So I make 1 the left child of 4. The next number is 29. 29 is less than 60. So I move to the left. And I come to 12. 29 is greater than 12. I move to the right. I come to 41. 29 is less than 41. But there is no left of 41. So I make 29 the left child of 41. Then I have 84. Start comparison with the root. 84 is greater than 60. Move to the right. Come to 90. 84 is less than 90. Move to the left. Come to 71. 84 is greater than 71. Move to the right, but there is no right child. So make 84 the right child of 71. The second last number is 23. Start comparison with the root. 23 is less than 60. Move to the left. Come to 12. 23 is greater than 12. Move to the right. Come to 41. 23 is less than 41. Move to the left. Come to 29. 23 is less than 29. But there is no left child of 29. So I make 23 the left child of 29. The last number is 37. Start comparison with the root. 37 is less than 60. So we move to the left and we come to 12. It is greater than 12. So we move to the right and come to 41. It is less than 41. So we move to the left. We come to 29. It is greater than 29. So we should move to the right, but there is no right child. So we make 37 the right child of 29. In this way, our binary search tree is complete. Traverse the tree in order fashion. Do you get a sorted list? This is one way to check a binary search tree. If you make a binary search tree and an in-order traversal does not give you a sorted list, then there is something wrong with your BST. The minimum value is in the leftmost node and the maximum value is in the rightmost node. In this tree you can see that the minimum value is 1 and the maximum value is 93. Balanced BST. When the difference in the height of the left and right subtrees is 1 or 0 or -1, the BST is said to be balanced. A balanced BST is the kind of binary search tree that we mostly desire because it has nearly similar number of nodes in the right subtree and in the left subtree. So a balanced BST is something like this. Here the height of the left subtree is 2 and the height of the right subtree is 1 and the difference between left and right is 1. This is another balanced BST. Height of both left and right subtrees is 2 and the difference is 0. And this is Another example where the height of left subtree is 1 and the height of the right subtree is 2. So the difference is -1. The three examples shown here are all balanced. Worst BST. The worst BST forms from a sorted sequence. Look at this BST. The sequence was 60, 90 and 93, sorted in ascending order. The smallest number became the root and all the tree hinges towards the right. There is no tree on the left. This gives us a tree whose height is same as its number of nodes. Another tree. This is also the worst BST that you can make. It has been formed by a sequence that was in descending order. The largest number became the root. So all the tree hinges towards the left. Any BST of width 1 would be the worst BST. Width 1 means every level has just one node. If you remember, width is the number of nodes in the most populated level. Both of these trees are width 1 trees. And width 1 trees have the same height as their number of nodes. And traversal takes a lot of time. A tree of width 1 is actually a linked list. It stops being a tree, it sort of degenerates into a linked list. Here is another example. Now this is the worst BST. It has not been formed from a sorted sequence. Still, since it is width 1, it is the worst BST that anybody could make. Homework 1. Build a BST for this sequence of numbers. 2. Traverse the tree in order fashion. 3. Write code to find the minimum value in a BST. The function is called minimum root. 4. Write code to find the maximum value in a BST. The function is called maximum root. This is code for searching in a binary search tree. The function is called search BST. It takes a node and a target value. If the node is none, it returns none, 0. Every time it returns a 2-element list. And this return value, none, 0, signifies that the search is unsuccessful. If node.data equals target, return node, 1. 1 signifies that target is present in the node that we are returning. If target is less than node.data, we will move towards the left subtree, and if it is greater than node.data, we will move towards the right subtree. In this code, if target is less than node.data, we will execute the body of the if, and if it is greater than node.data, we will execute the body of the else. Now let us suppose that target is less than node.data. Then we check if a left child is present. And then we check if data in the left child matches the target. If data in the left child matches the target, we return node, 2. 2 signifies that the target is present in the left child of the node that we are returning. But suppose that the left child does not contain target. Then we update node to the left child of the node. If the left child is altogether not present, then we return none, 0. Again, this means that the search is unsuccessful. Now come to the else part of the third if of the code. This executes when target is greater than node.data. So first we check if there is a right child, and then we check if target matches data of the right child. If node.rc.data is equal to target, return node, 3. 3 signifies that target is present in the right child of the node that we are returning. But if target does not match data in the right child, then we update node to the right child of this node. If the right child is altogether not present, then we return none, 0, which means that the search is unsuccessful. At the end of this whole thing, we recursively call search BST. The target remains the same, but the node has been updated. It is either now the left child of the previous node or the right child of the previous node. So when we are searching in a binary search tree, search proceeds in only one part of the tree. From the root, it goes to either left or right. Then from the next node, it goes to either left or right. So we don't search the whole tree, we only search one subtree of each node. Let me show you an example. I am trying to find 83 in this binary search tree. I start with the root and I compare 83 with 60. And then I find out that 83 is greater, so I should move towards the right subtree. So I will call the search function again for the right child of 60, which is 90. Again I compare 83 with 90, and since 83 is smaller, I will move to the left subtree of 90. So I will call the search function again for 71. Now I compare 83 with 71, and since 83 is larger, I call the search function again for the right child of 71. So now I am at 84. I compare 83 with 84. 83 is smaller. So I should move to the left subtree of 84. But there is no left subtree of 84. So this means that 83 is not present in this BST. I want you to find 29 and 36 in the same way in the given BST. Let us look at the time and space complexities of searching in a binary search tree. In the worst case, we call as many recursive function instances as the height of the given tree, and the number of activation records pushed onto the runtime stack is h minus 1. From this, I can deduce that the time and space complexities for searching in a BST are both OH, where h is the height of the tree. If you have the worst BST, then h would be equal to n. For most balanced BSTs, h is nearly equal to log n. Deleting from a binary search tree. If the node to be deleted, we call it the victim. If the victim is a leaf, simply go to the parent of the victim and set the relevant pointer to none. If the victim has one child, make the parent of the victim adopt the victim's child and then delete the victim. If the victim has two children, find its logical successor. If the logical successor has a right child, it is adopted by the logical successor's parent, and the data value of the logical successor is copied to the victim's data field. The logical successor is deleted. The logical successor of a node is the minimum value in its right subtree. Let us delete 23 from this BST. First we use the search function to locate 23 and we find it here. Then we realize that 23 is a leaf. So this is very easily done. We go to the parent of the victim, which is 29. The left pointer of 29 points to 23 and we will set this to none. And 23 is deleted. So deleting a leaf is very easy. Now I want to delete 41. I call the search function and it locates 41 here. But 41 has a child, which is 29. How can I delete 41 and how will I adjust 29 in the tree? I first locate the parent of 41, which is 12. I make the parent of the victim adopt the orphan of the victim. So I make 12 adopt 29 as its right child. This is what I want to do. Now 41 has been deleted from the tree and 29 becomes the right child of 12. Now I want to delete 12. I locate 12 to be here. 12 has two children. Now the strategy of making the parent adopt the orphans will not work here because there are two orphans and the parent can adopt only one child. So now I will locate the logical successor of 12. The logical successor of a node is always found in its right subtree. The right subtree of 12 is rooted at 41. The logical successor is the minimum value in the right subtree. The minimum value in the right subtree of 12 is 23. So 23 is the logical successor of 12. Notice that 23 does not have any children. Since 23 is a leaf, it is easy to delete it. What we do is we copy the value of 23 to 12 and then we delete 23. And in this way 12 is deleted. I want to delete 60 from this tree, which is the root. It has both children. Locate the logical successor of 60. Find the minimum value in its right subtree. The minimum value is 71. So 71 is the logical successor of 60. But 71 has a child of its own. So we make the parent of 71 adopt the orphan of 71 in this way. Now I am going to copy the value 71 to the node containing 60 and then I will delete the node containing 71. In this way 60 has been deleted. Try yourself and delete 90 from this tree. Things that we learned today. We used heaps to sort data. We learned to build binary search trees. We learned to search in a binary search tree. We learned to delete in a binary search tree. And we examined all codes for time and space complexities. Please read the book, do the homeworks, note your questions, and email me your suggestions. Take care. Allah Hafiz.